Hello all, I welcome you all to the 21st lecture, this course E690 ATM. Till last time we saw about electrons and its scattering with photons, phonons and so on. But one particular aspect which has been common with all the lectures that we have seen is that we have assumed there are no electron interactions. Beginning with the Drude's model, we assume that there are no electron-electron interactions other than the fact that Pauli's exclusion principle holds. Right? We have always used this. In addition to this particular aspect, we have also included electron interactions in one other place, or probably actually two other places. Another one where we actually did not deal with in depth, but we just considered another influence of other electron, which is the screening effect. Correct? Where we said that any potential V will be transformed into V into e power minus lambda into R. Right? And lambda is the screening parameter. And this happened because, let's say, we take a material and we put a positive charge in the material, and any free going electron is affected by this potential, not by the actual Coulombic potential V, but some reduced potential. That is because there are other free electrons which go and cloud this positive charge, thereby screening it effectively. Right? So this is one effect of electron-electron interaction that we have considered. The other one that we saw but then we did not deal with in a lot of depth is the plasma oscillations. We did not go into a lot of details because we really do not need this for the purpose of this course. We did not deal with surface plasmons and plasma oscillations. We just only showed that under certain electromagnetic interactions, the dielectric constant, which is proportional to the frequency, has 1 minus omega by omega p kind of a behavior. And omega p is called the plasma oscillation frequency. It is in this frequency the electrons act collectively with the response of with the interacting electromagnetic radiations, right? So this is once again an electron-electron interaction, but it is due to an external perturbation, right? But in all other cases, when we derived the band structure, when we derived the solutions for the Schrodinger equation, we have always assumed that there are no electron interactions. When we had electron dynamics, like electron transport behavior with Boltzmann transport equation, we had this assumption, right? How do we know this assumption is true? There are some interesting aspects. Let me do this very simple calculation, right? Let's say an alkali metal, alkali, sodium, potassium, or alkali metals. Let's take an alkali metal. The typical density is the atomic density, right? Every atom has one electron, is to the 23 per centimeter cube, approximately, not in the same order but approximately, right? And this in a material kind of gives you an electron separation of 2 angstroms. So think about it. You have two negatively charged particles separated by 2 angstroms. So what would be the Coulombic potential that an electron will face? Is going to be phenomenal, right? Because 2 angstrom is such a small value. It is close to the interatomic distance, right? So under such situations, why don't you see the effect of electron-electron interactions? Why don't 2 electrons scatter? We have assumed that they do not scatter, right? Experimentally, we have been observed that the mean scattering length we always go back to this, right? Because this is how we used to say that the Drude's model is not accurate, but even here we used to say the mean scattering length is about 1 micrometer for a pure material at room temperature, and at about 10 centimeters at about 1 Kelvin. And this is very large in comparison to the electron-electron separation, which is 2 angstroms. But even then, right, all we have shown previously that the very simple non-interacting Fermi gas is called as a Fermi gas, right? A collection of electrons which follow Fermi-Dirac statistics where the interactions have been neglected is called as a Fermi gas. A very simple non-interacting Fermi gas explains most of the properties of metals. The question is why? Given these facts that the electrons are very close to each other, still they don't seem to scatter. There is not much of an influence in any of the parameters like thermal conductivity, electronic transport, and so many other factors, electron absorption, electromagnetic field absorption, and so on. The main reason, or the two main contributors to the fact that the electrons do not scatter is Pauli's exclusion. We will soon see why Pauli's exclusion is so important, not only in the way electrons are distributed, but also in the way they can get scattered. Second, but not so dominant, screening. Because of the fact that there are so many electrons around, these electrons also screen the other negative potentials, right? So there is also screening from other electrons. So now let's look at some simplified picture to understand how the Pauli's exclusion principle comes into play, or helps us to show that the non-interacting electron picture is good enough for most of the solid state physics experiments. So for that, we are not going to go into this multi-dimensional electron-electron scattering. We are once again resort to only simplified 2-electron behavior. Let's see what this guy gives. Okay, so because we're talking about 2 electrons, I'm going to take the first electron to have the following properties: K1, E1. The second electron has K2 and E2, right? And these 2 electrons are now going to interact, right? And in any interaction picture, we can draw the Feynman's diagram. I have not given you any background about Feynman's diagram. I'm just not looking at the Green's function propagation and such, just looking at the way the interactions work, right? So I just use it as Feynman diagram, but I don't really use it to do any calculations as such. So let's say that I have first incidenting electron, which is 1. Second electron, they both interact at one point. Second electron, they get scattered to 3 and 4. Right? Obviously, the particles have to be number conserving. You don't lose any particle in any interaction. So they get scattered to particle number 3 and particle number 4. And once again, as described previously, let's say this gas wave vector K3, energy E3. This has wave vector K4 and energy E4. Now it's easy to see it's a second order process, right? You have 2 particles interacting at the same time in space and time, right? So this is basically a second order process. In any second order perturbation theory, what is conserved is not individual electrons. Let's say electron 1 got scattered to electron 3. In the first order process, you would say that E1 should be equal to E3 plus the scattering, right? Some whatever h cross nu. And let's say 2 got scattered to 4. You will say that E2 will be E4 plus h cross nu. This is the first order process, but we are talking about the second order process because both of them are interdependent. You do not have E1 scattering without the presence of E2. So now we have what is called as a second order perturbation, second order scattering. And in the second order scattering, only the summation is conserved. What we mean is E1 plus E2, that is the summation of the electrons which are getting scattered, should be same as E3 plus E4. After scattering, the summation, the energy is something like this, because there is no loss of energy. There is no additional phonon, no additional photon, none, no such, right? Just two electrons getting scattered to another two electrons. Similarly, the wave vectors should also be conserved. So K1 plus K2 should also be equal to K3 plus K4, right? So given these constraints, I'm going to take a look at the K-space distribution, right? So once again, let's say we are at 0 Kelvin. At 0 Kelvin, all the electrons, all the states below the Fermi wave vector are filled. So let me draw this K space. This is Kx, this is Ky, and Kz, right? It's difficult to draw the sphere in the 3 dimension. I'm just going to draw the circle in 2 dimension. It's up to you to assume a 3-dimensional sphere here, right? So this is the Fermi sphere. What is the meaning of Fermi sphere? All states below this, inside this sphere, are occupied. That's what Fermi sphere basically means, right? So, and this is Kf. Now I'm going to take two electrons. Let's say one is outside the sphere, that is K1 is greater than Kf, and 2 is inside the sphere, that is K2 is lesser than Kf. I'm going to see scattering between these two. Why one is taken to be outside, that we will see soon enough, right? So I will show that this is necessary. You should at least have one electron outside the sphere. Now why this should be true? So I am taking K1 greater than Kf and K2 lesser than Kf. Another way to write it, because they are square dependent, E1 should be greater than Ef and E2 is lesser than Ef. Under these situations, one must see that these get scattered to states 3 and 4, right? And remember, so let me draw it in the different color. Let's call this 3, let's call this 4. Remember, 3 and 4, K3, K4 should be greater than Kf, right? Why? All these states within the Fermi sphere is occupied, and only thing which is for the electrons 1 and 2 to be scattered away are the vacant states above Kf, right? So K1 and K3 and K4 should be greater than Kf, since all states below Kf are occupied. Another way to write it, E3, E4 are greater than Ef. It's easy to see that all of them are benchmarked across Ef. So I'm going to take Ef to be 0, or I'm going to refer all the energies with respect to the electron Fermi energy, right? So in this case, it's easy to see E2 is negative, E1 is positive, and E3 and E4 should be positive. Right? So given that E3 and E4 should be positive, so the right hand side of this conservation law is a positive quantity. They should not put an A. Right? Therefore, E1 plus E2 should be positive. right? There is no other way. So what it means, summation of energies E1 and E2 should be positive, and if it clearly means one of them should at least be outside the sphere, right? Both 1 and 2 cannot be inside the sphere. So this is a very important observation for the, so once again let me repeat, E1 and E2 are referenced with the Fermi level, right? So the summation should be greater, should be positive, and this is only possible that at least one of them should be outside the sphere. Both of them being inside the sphere, both of these values E1 and E2 will be negative. Summation of two negative quantities can never be positive. Therefore, at least one electron should be outside the sphere, Fermi sphere, right? So that given, that is the reason why I took one outside. Now the two can be inside, right? Now let's say if E2 is negative, E1 is positive, as we saw previously. This is the consideration that we took. Now for E1 plus E2 to be positive, magnitude of E2 must be lesser than E1, right? E2 is negative. So what is the excursion of E1 from the Fermi sphere? Let's say this, and this separation is E1, right? And if I draw some imaginary subsphere which is offset by E1, 2 should lie within this sphere, within in this shaded region, right? If the 2 does not lie within this shaded region, that is the second electron should have energy only within this shell, right? If it has energy somewhere here, it cannot get scattered, right? There cannot be any scattering event. Thus the electron scattering cross section is now severely reduced. Remember, it is reduced by the extent in which one is outside the sphere. If I have one very large, very far away, then it can have any electron to be scattered. If I have one very close to the surface, then the scattering possibility is now reduced to a very small region surrounding the Fermi sphere, right? Therefore, the scattering cross section, which is denoted by sigma, is now severely reduced. The reduction is dictated by the excursion of the first electron from the Fermi surface. So let's take one simple example. Let's say the excursion from the Fermi surface, how far this excited electron can be away from the Fermi surface, is obviously dependent upon the thermal energy, right? Eventually thermal energy is what gives you how much far away this can be away from the surface. So let's say that let's say this E1 is somewhat close to kBt, and the scattering cross section is now reduced by the sigma, is the scattering, new scattering cross section is now reduced by the energy excursion kBt square by the actual Fermi square. So this is EF, the extent, right? And if let's say the constraints of scattering is not imposed, then the total cross section will be EF cube, EF into square, right? So now we're talking about some shells, and the other one is KBT square into sigma naught, that is the normal or unaffected scattering cross section. So now let's say we are at 1 Kelvin. The typical Fermi is about 5 into 10 to the power 4 Kelvin. The typical Fermi, the energy of the electron at the Fermi level is about 5000 Kelvin. This is something we derived during our previous lectures. I would request you to go back. And at 1 Kelvin, the KBT is, let's say, again 1 Kelvin, right? So the ratio sigma by sigma naught at 1 Kelvin is reduced by 4 into 10 to the power minus 10. That is, the scattering cross section is reduced by 4 into 10 to the power minus 10 times the normal Fermi C. Let's say the Fermi C has about 10 to the power 23 electrons. An electron can get scattered only about 10 to the power 13 electrons. That's the only probability that you can have. Other electrons you just cannot access, right? So that's what this guy means. At room temperature, the same sigma by sigma naught is about 10 to the power minus 2. Obviously it depends upon this, right? And the scattering cross section is about 10 to the power minus 2 square into sigma naught, which will 10 to the power minus 4 into sigma naught. And if there are 10 power 23 atoms, and the mean scattering length is 1 by n into sigma, which is 1 by, let's say, 10 to the power 23 into 10 to the power minus 4 divided by 10 to the power 23, which will give you 10 to the power minus 4 centimeters. So the total scattering length, which is just dominated by electron-electron scattering at room temperature, L turns out to be about 10 to the power minus 4 centimeters, which obviously is too large, right? So the typical scattering length, as we saw previously, is about a micron, and this is almost a micron, right? So this is what we saw. Our previous claim was the typical mean scattering length for very pure electrons at room temperature is about minus 4 centimeter, and we came here. But at room temperature, the scattering or the mobility is mostly not dominated by electron-electron scattering, but electron-phonon scattering will become the most dominant one. But let's not go into that right now. So with very simple calculations, we have come to this conclusion that the mean scattering length for electron-electron scattering at room temperature is 10 power minus 4. So basically an electron will travel at room temperature about a micron before it gets scattered by another electron. Even though an electron are very close to about 2 angstroms, this is when they will scatter, right? Now, in addition to this calculations mean scattering lifetime that we saw, one has to remember that the scattering rate depends on the energy of the electron from the surface if the energy of the electron is taken to be E, the mean scattering lifetime is given by or is proportional to E square plus, this is inverse of mean scattering lifetime, right, plus pi square t square, and which means at t equal to 0 and then and an electron at the Fermi level will have an infinite lifetime. Right? So let's just take a look at this aspect once again. I'm going to once again draw the Fermi sphere. Right? And as we saw previously, this is kx, ky. This does not really matter. And let's say I take an electron outside, another electron has to be inside, and it goes like this, right? And this is true, and the probability for it to scatter because of the summation criteria as we saw previously can be obtained by this center of mass behavior. So you take a center point with equal exertions from both the sides and draw a sphere, a circle around this, right? And 2 points, now let me draw the other one in red. The 2 points which sit at diagonally opposite sides are the only ways in which it can scatter, right? This is the way it can be observed, and any other, this is not allowed, right? Because this state is already filled. Only states outside the sphere are allowed. So only these two, or only this small area is what will be allowed for scattering. Correct? This is what we discussed previously. And given, so this area depends upon how far this exertion is from the surface, right? And if this exertion is on the surface, then the scattering probability for it becomes 0. It just have no other place to get scattered. So an electron on the surface will have an infinite electron scattering lifetime. Electron on the Fermi sphere will have infinite electron scattering lifetime. And at 0 Kelvin, obviously you have very long lifetime, and at any other temperature such electrons will have really long lifetimes, and these electrons are called quasiparticles. Quasiparticles are the names which are given to particles which are similar to a particle, but they are not exactly a particle, right? So here, an electron which sits on the surface and which is interacting with all the other particles cannot be thought of as another particle, but this is what Landau called as quasiparticle, and such a distribution Landau called as a Fermi liquid. Landau Fermi liquid is a particle, is a collection of weakly interacting because they are interacting only in the sense of scattering probabilities. They are not interacting very strongly, weakly interacting Fermi gas, right? And they are called as quasi-particles. In the Landau's theory, there is one important aspect that we will see before we close this, because we will not go much deeper into Landau's derivation and such, because it will require a treatment of initial, like second quantization and quantum field theory. We will not go into such details, but there is just one thing that I would like to say before we quit this topic on Landau liquids or Fermi liquids, because you might hear this term as Fermi liquids in, let's say, transport in at very low temperatures, transport in nanotubes, transport in very pristine materials where scattering with phonons and scattering with defects are not present. Electron-electron scattering will start to become more dominant. Under such situations, you will start to see liquids and Littinger liquids and so on and so forth. But but this is the picture that Landau painted, that one can actually shift. One can shift from non-interacting Fermi gas to a weakly interacting picture adiabatically. What he means by adiabatically is you move it so slow that there is no exchange of heat. That so basically you have so let's say here you have a Fermi sphere with a collection of electrons and its states which are not interacting, right? And from here you turn on a knob where the electrons and electrons start to interact. Under such picture, you can transform from this non-interacting gas to an interacting Fermi liquid picture adiabatically. And in such situations, there are certain things which will remain unchanged. Landau predicted the momentum, spin and charge of the electron to be unaffected by the interaction, and what gets affected is the energy, the wave functions, the mass, effective mass, and effective magnetic moment. Gets affected because of these interactions. So let's say one can move from the block electron, free electron picture that you will have when electrons are not interacting. From there you can move adiabatically to a system where the electrons are weakly interacting by keeping the momentum, spin and charge of the electron unaffected, and the energy levels, wave function, effective mass and the effective magnetic moment in the new system with interaction slightly changed from the original uninteracting picture. Now how they are changed, how to move from one to the other are things that we are not going to cover here. It is just to show that one can actually tweak the non-interacting picture that we have handled till now into an interacting picture, and there we start to call the electron distribution no longer as a Fermi gas but as a Fermi liquid or Landau Fermi liquid, right? And these energy levels are called as renormalized energy levels, wave functions, effective mass and so on and so forth, renormalized with interactions, with electron-electron interactions, right? So this is a very short and a brief treatment on electron-electron interactions and Landau Fermi liquid. With this weak or very very simple treatment on electron-electron interactions, we will see one important application where electron-electron interactions are significant, are very important, right? It cannot be described by the one particle picture, and that is superconductivity. I did this electron-electron interaction picture just so as to introduce the fact that if you ever have to deal with superconductivity, you cannot explain superconductivity unless you start to include strong electron-electron interactions. And in the next lecture, we will deal with superconductivity. Thank you.